just go back to the last class discussion. We had the idea of operation, not the more engineering details, because engineering details is difficult for this class. But anyway, you have understood that the objective was to extract as much waste heat as possible by improving the heat transfer between two gases. One is being cooled, another is being heated. And in that process, the difficult challenge was gas to gas direct heat exchange through a conducting surface. That's the standard practice. We call it recuperative heat exchange. In there, the hot gas flows through one channel or tube, or the cold gas flows surrounding that particular tube or channel. Then obviously the conducting material of the tube or channel allow heat transfer without getting these two different fluids mixed. In some cases, direct mixing is one option, but in direct mixing, though the heat transfer is maximum possible, but it is actually in industrial applications, it happens in very limited cases because contaminations of these two sources of gas and the receiving gas doesn't allow this particular direct mixing. So indirect heat transfer is a general picture. And in indirect heat transfer mode, in the last discussion through heat pump, we have understood that by converting the gas to gas heat exchange to 2 TWO2, two phase heat exchange, subsequently, one is by the evaporation process, another is subsequently by the corresponding condensation. So, these two phase heat exchange means the working fluid changes its phase from vapor to liquid and then again liquid to vapor. And during this conversion of either liquid to vapor or vapor to liquid, the heat transfer coefficient increases several times, even sometimes thousand times, several thousand times also happen, rather than the conventional single phase heat transfer. So obviously the overall heat transfer increases to a great extent. Just by introducing the mechanism in heat pipe. So heat pipe is a very active area of research. Developing very efficient heat pipe at different industry level, and you have finally seen that particular picture, that heat pipes operate generally in a cluster means several heat pipe mounted on a frame structure. Anyway, after this, now I'm going to the next, another innovative option of increasing the waste heat recovery is this one. This is the rotating regenerator or heat wheel. What is the idea is, previously we have discussed about the recuperative heat exchange. Maybe I'll give some initial text of this, but just try to understand the previous heat transfer process where two gases simultaneously flows and they are separated through a conducting material surface. It can be in the form of a tube, it can be in the form of a channel of different sections, maybe rectangular section, maybe square sections, whatever it may be, maybe elliptical sections. But the definitions of recuperative is that whatever heat exchange happens between two working fluids, they both are simultaneously flowing through different channels and separated by a surface. But this is the regenerative heat exchange process. What does regeneration means? Regeneration means whatever heat you will use by any cold gas, that will not simultaneously flow through the same channel. That obviously there will be a cyclic process of heat receiving and then heat discharge by the so-called matrix. So let me just explain it fully. Before that, just write down short note about that recuperative. I have not mentioned specifically for the previous heat exchange process, but most of the cases it is recuperative. Just write down recuperative heat exchange, RECUPERATIV. Recuperative heat exchange is the process. Recuperative heat exchange is the process of heat transfer between two working fluids, flowing simultaneously and separated by a conducting surface. Separated by a conducting surface. Full stop. It is an indirect heat exchange process. It is an indirect heat exchange process without any direct mixing, without any direct mixing of the two heat exchanging fluids, of the two heat exchanging fluids. Full stop. Recuperative heat exchange, next sentence, recuperative heat exchange is most predominant mode of heat exchange most predominant mode of heat exchange of and pressure difference between two fluids can also be accommodated, and pressure difference between two fluids can also be accommodated in recuperative heat exchange. However, heat exchange amount heat exchange amount in this process depends on heat transfer coefficient heat transfer coefficient at both sides of the heat exchange at both sides of the heat exchange and flow characteristics and flow characteristics and physical properties flow characteristics and physical properties of heat exchanging fluids. Full stop. Some special arrangements for creating more turbulence for creating more turbulence, turbulence, within bracket, say by adding baffles, say by adding baffles, and increasing the increasing the time of heat exchange, time bolo na, duration bolo, increasing the duration of heat exchange by arranging flow paths, PATHs, recuperative heat exchange may be increased. Full stop. In addition, innovative ways of special measures within bracket, say in heat pump, so say in heat pipe, say in heat pipe and heat pump are completely different things. Within bracket, say in heat pipe, bracket closed, recuperative heat exchange may be enhanced. Recuperative heat exchange may be enhanced. So I'm just what I've told in summary, if I just make it, because I know it's a mixed group, the recuperative heat exchange, by definition, two fluids will simultaneously flow and they will have heat exchange between due to their temperature difference and separated by a surface which is conducting surface, obviously. And depending on the characteristics of the fluid between which the heat transfer is happening, you can have different heat transfer. That is one characteristics, is the fluid characteristics. And then the fluid characteristics of both its physical characteristics, its physical properties. Characteristics and properties, how I'm separating or identifying. Properties are, say, its specific heat, its viscosity. These are the physical properties. But on the other hand, what is the velocity? What is the corresponding Reynolds number? How much is the turbulence? These are the characteristics. So obviously, as I'm telling, the mathematical part I cannot cover in this class, but still you can understand that by creating some, and again, the amount of heat transfer, that's a common sense, that if two fluids are exchanging heat through a separating conducting surface, then if you can increase the contact duration, means rather than say 10 seconds, if it is say 30 seconds, then automatically the heat transfer will be more. And somehow within a given volume. Why given volume? Interesting part is volume is an indicator of the total cost of the device, because volume increases means obviously that needs more material. So for a given volume, if you can somehow increase the contact duration between the two fluids, then automatically you will have better heat transfer. But in addition to that, increasing turbulence means what? Very organized fluid flow is not helpful for more heat transfer. Rather, the very what we call the turbulence is measured actually by the velocity and simultaneously the random motions of the liquid particles. And there are very precise definitions of turbulence measurement by different instrument and the physical process. But those things actually are not covered in a mixed group. I am not going to mention these things. But if you can create turbulence in the fluid, that also increases the heat transfer coefficient. So these are the possible all different options. And in addition to that, there are some special measures like whatever you have experienced in the heat pipe, that converting the overall recuperative heat exchange through, two consecutive two-phase heat exchange process, we have increased the heat transfer. Now, today we're going to discuss another device. I may not be able to discuss all the possible options of the waste heat recovery, but some sample devices I will discuss just to give you an idea how innovative processes of waste heat recovery can happen with better improvement, because engineers are always given the challenge of overcoming the restrictions as far as possible, and that again must be justified against cost, and that part in waste heat recovery, what we call it waste heat recovery economics, will come at the end. Anyway, so now I'm going to the next paragraph, which is called regenerative heat exchange, which is the basic principle of this topic, rotating regenerator or heat well. So just go to the next paragraph. In regenerative heat exchange process, in regenerative heat exchange process, hot and cold working fluids, hot and cold working fluids flow alternately, flow alternately through, THROUGH, through a high heat capacity, through a high heat capacity matrix, MATRIX matrix, full stop. In this process, matrix is heated during hot fluid flow during hot fluid flow, extracting waste heat. Full stop. In subsequent cycle, in subsequent cycle, in subsequent process, though it happens in a cycle, in subsequent process, cold fluid passes through this heated matrix to gain this, to gain GAIN, gain this heat added to the matrix. Thus, next sentence, thus, in a repeated cycle, thus in a repeated cycle of heat addition and extraction, heat addition and extraction to TO2 to and from the matrix, to and from the matrix, effectively makes the heat transfer process makes the heat transfer process between two TWO, two fluids. So, next sentence. So, in regenerative heat exchange, regenerative heat exchange process, though two fluids, though two fluids do not simultaneously flow, do not simultaneously flow side by side, contamination, contamination, contamination of any fluid may be transferred, may be transferred to the other fluid as both fluids alternately flow through the same matrix. Full stop. Moreover, increased heat transfer, increased heat transfer through the matrix, through the matrix may increase more contamination as both both needs very close contact between the gases and the matrix, between the gases and the matrix. Okay, so if I just, after giving the text, if I look into the situation, what is happening here, I mean, I'm yet to start the how the regenerative heat exchange process is implemented in the device which is named as rotating regenerator or heat well. But before that, I thought that it will be necessary, because it's a mixed group, how the recuperative and regenerative heat exchange are defined. So you have understood the recuperative heat exchange very clearly, I'm sure. Two fluids simultaneously flow with a temperature difference by a separating surface, conducting surface. And here in regenerative, they are not simultaneously flowing. There is a particular material which is called matrix, through which alternately heated fluid and the colder fluid, I mean hot fluid and cold fluid, will pass. So what will happen when the hot fluid passes? If the matrix has got very high heat capacity, or as far as possible heat capacity, then automatically the heat will be retained, not all, but some part, during other, as if the matrix will be heated by the hot gas flow. And then if that matrix is subsequently exposed to a colder gas due to temperature difference, the matrix will release the heat to the gas. So as if it's the recuperative direct transfer from the hot gas to the colder gas through a conducting surface. But in regenerative, not direct. Alternately heating and then alternately cooling. That means matrix is intermediate media or agent for the heat transfer process by subsequent heating process through hot fluid and cooling process by a colder fluid. And now the challenge of regenerative heat exchange is greater challenges basically, which is not at all present in recuperative, is the contamination problem. Because as I have mentioned, that no industrial fluid, whether it is a liquid or gas, whatever it may be, specifically for waste heat recovery, it is coming from a previous upstream process. Means what? It has done the actual process which is required. For example, in metallurgical metal extraction process, the waste heat is generated by the metal extraction process itself. So the primary objective is not waste heat recovery. Primary objective is the metal extraction process. But for that process, whatever hot flue gas is generated, that eventually has to be contaminated. Means carrying lots of dust and other many particles, including many obnoxious gases. Now, the difficulty of this recuperative heat exchange is, from that viewpoint of contamination, absolutely free, because they are not coming in direct contact, whatever. But that can cause some depositions, and that actually call the scaling formations, etc. These are separate problems. They're also under the engineering issues, how to clean those surfaces, etc. The chemical engineers and mechanical engineers work always together regarding these issues, and these are also very active area of industry research and the activities. But in regenerative heat exchange, the main problem is alternately hot gas or hot fluid, it can be liquid also, flows, hot fluid and the cold fluid alternately flows to the same section. Then the problem is, if the either hot gas or cold gas has certain contaminations, not for gases that happens, because gas passes out means only it can make some reaction in the matrix, and that the material has to be chosen such that it doesn't have any reactions with the gases in that particular hot gas mixture or cold gas mixture. But if there are some carrying dust particles or say acid droplets, etc., then what will happen? These will be automatically deposited, or rather remained or retained by the matrix during the flow of corresponding gas. It can be in the hot gas flow, or it can be in the cold gas flow, specifically in the hot gas flow, because cold gas flow may be in most of the cases atmospheric air. So though it contains dust, but anyway, that's the acceptable value. I mean, not that difficult that it is too much dust loading. But if the hot gas is a metallurgical extraction process hot gas, then invariably it will be too much dust load will be there. So it will get deposited into those matrix. And then subsequently, when you are passing the colder gas, it will carry a partial, if not full amount of contamination. So the heated gas, you have not only received the heat, but also you have received some contamination from the heating gas. In that case, you have to have a very, so-called balanced approach. How much heat exchange you need, because from your common sense now, if you apply, how the more heat transfer can be obtained, if more heat can be extracted from the hot gas and that can be transferred to the cold gas. More heat extracted means the hot gas must be in very close contact with the matrix. And more contact means what? The gas loaded with dust, automatically it will be deposited on the matrix surface, and that will be automatically carried to the colder gas during heating cycle. So with this input, that means realizing that regenerative heat exchange process is name is coming from the regeneration process of the matrix through which the actually heat transfer happens. Regeneration means continuously getting the heat and then releasing the heat. This is the process of regeneration. And then we are entering into the device. So if you look into the device, just 1 minute, I'm going to Fanta Cellini. So now if we look into the device, you see that there are two parallel ducts. This is one duct, this is another duct. The duct may be of square or rectangular cross section. And through one duct, continuously there is a hot gas in, after the hot gas in, it passes through this so-called matrix. But matrix is not only a matrix, but it is in the form of a rotating wheel. I'm just trying to understand the physical process, then I will go to the rather little bit more in the next slide. So as if we have a wheel made of metal through, and there are holes through this wheel so that any gas can pass through the holes of this wheel. Now what will happen? If a gas passes through the holes of this wheel, then if its temperature is different from this material of the wheel, then automatically some heat transfer will happen to this wheel. Now question is, if it is heated, then next subsequent cycle, as per the regeneration heat exchange process, when the cold air come in contact with this heated matrix, it will take away the heat. So cold air in, warm air out. Now the question is whether it should be we call it batch process and continuous process. What do you mean by batch process? Batch process means it is a wheel, but just retain for say 5 minutes for the hot gas to continuous flow through this matrix and don't rotate. That means continuously 5 minutes, maybe this matrix part of the wheel is being heated. Then maybe you stop this hot gas flow or directly shift it to this part where the cold air starts flowing. Then what do you expect? Next 5 minutes, obviously the heated matrix will transfer heat to the low temperature air that is coming in. I'm assuming that air is being heated. It can be any other gas. Now, if you just don't do it simultaneously of the heat addition and heat rejection process, then I call it a batch process, BATCH. And if it happens that the wheel is continuously rotating, obviously at a very low RPM, because if you make it very fast, then no heat transfer can happen and effective time will not be there. But if the wheel can rotate with continuously with a very low RPM, then what is expected? The batch process is rather replaced by a continuous regenerative heat exchange process. Rather, regenerative batch heat transfer or regenerative continuous heat transfer process. In industrial applications, both examples are there, but generally continuous process is more common. That means if you want to rotate the wheel, and don't think these are very small one, these are very big one, to get sufficient heat transfer process, because otherwise the amount of heat gained will not be very effective, or rather investment cost will not be very much useful. So now the question is, if it happens with a constant very low RPM, then as if the matrix is getting continuously heated at some part of the wheel, and simultaneously that is being transferred to the parallel duct where the heat is being transferred. And in this example, you can find out very clearly that any contamination, if it is with hot gas, that will be retained by the matrix and that may be transferred partially to the cold gas when during the regeneration or cooling process. And also there is another issue. There is a leakage between the two gases. Because if it is a wheel, obviously it is, you have gone through the engineering drawing classes, it's in section, the drawing is in section. And then obviously you can, rather it is in half section drawing, you can look into the picture that here is one gas flow, here is another gas flow. And in between there must be a portion which, where if there is a pressure difference between these two gases, there, because gas will always try to flow from high pressure to low pressure. So if there is a pressure difference between these two gases, if not any pressure difference, then also the diffusion effect will be there. So being two gas simultaneously exposed to this rotating wheel, you can expect that there will be a mixing of these two gases possibility. So in between these two flowing gases, proper sealing has to be there, which are called radial seals, so that the gas from one duct will not be allowed or rather able to pass to the surrounding side by side duct. Providing this sealing properly is also another very associated important aspect. Otherwise, no heat transfer will happen through the regeneration. Directly gas mixing will happen through this radial gap. So the important issues, if we just look into, so maybe I can give a small description, because I know that there is no, I mean, single textbook for covering this entire energy conservation. So just write a short process. And there is another issue I must mention before I give the text. These are called circumferential seals. One is the radial seal, another is the circumferential seal. What will happen in circumferential seal is, during heat transfer, you can understand, there will be during heat transfer and simultaneously gas flow, automatically there will be some pressure drop, because it is passing through some holes. Because you know, any liquid or gas, if it flows, always there is a pressure drop. And from that pressure drop condition, what is happening at downstream side, always the pressure will be lower, whatever small difference, and the upstream side the pressure will be little bit higher. So there is a pressure difference between the upstream and the downstream side. Now, if in the radial section, because if it has to rotate, the cover, between the cover and the wheel, there must be some gap, otherwise it will foul with the cover. So when it rotates, if you allow, if the rotation has to be allowed, then there must be a gap between the cover, we will call it shroud and this particular wheel. So then what is happening? If you provide this gap, then obviously the gas will have either side, this side or that side, as the pressure here is higher and here low, rather here higher, here low. Due to the pressure difference, gas will have a tendency to flow through the outside circumference. So the circumferential seals is also important. So circumferential seal is required to prevent the leakage of gas, or leakage of the same gas bypassing the wheel, and radial seals are required to arrest or resist the flow of either of the gas to the other section depending on the pressure difference. So these two seals and the matrix material and the other physical parameters like gas velocity, RPM, these are the important issues in the engineering design process of the rotating regenerator of the heat well. So let me give a small description for your examination purpose that will help you for understanding. Just write down. Rotating regenerator or heat wells, rotating regenerator or heat wells are made with metal frame, FRAME, metal frame structure filled with, FILLED, filled with different types of, filled with different types of matrix for effective heat transfer process. Next sentence. As there is as there is always a pressure drop, as there is always a pressure drop as the fluid passes through the matrix, there will be a tendency of leakage of gases. There will be a tendency of leakage of gases through the circumferential gap, through the circumferential gap between the shroud, shroud, shroud of the heat wheel and the heat wheel itself, and the heat wheel itself. Full stop. This has to be minimized by providing circumferential seals which allow which allow gas to flow through the matrix minimizing gas leakage through the circumferential passage, through the circumferential passage between the shroud and the wheel. Full stop. On the other hand, comma, there will always be a possibility of flow between two heat exchanging fluids through the radial passage of the wheel. Through the radial passage of the wheel at the center. Full stop. This increases with pressure difference between two heat exchanging gases, fluids level, between two heat exchanging fluids. This increases with pressure difference between two heat exchanging fluids. Radial seals take care of this radial leakage. Radial seals take care of this radial leakage. Okay, so now I'm in what condition? If you have any queries, you can anytime ask. You have understood the regenerative heat exchange process, where the same matrix will be alternately heated and cooled by the two heat exchanging fluids. What are the issues to be addressed? The basic important issues to be addressed is we have to design it such a way, because engineering means design always. We have to design the system in such a way so that the heat transfer to the matrix to either of the gases is enhanced. And we have understood that the inherent challenge of these gases are two types of leakages in this process, not the gases. In an inherent process of the regeneration process is the leakages. That means how it in the same fluid leakage bypassing the wheel itself can happen through the circumferential passage. On the other hand, the leakage between the two fluids can happen in through the radial passage, so providing seals. But the another important problem we have posed, and we will see how there is a conflicting interest between the heat exchange and the contamination, because the same surface or same matrix will be exposed to the both fluids in a cyclic process one after another. So now, unless we discuss the matrix structure, different possible options, we can't just explain it very clearly, because the close contact of any gas with the matrix is very much required. But close contact means any impurity present in the gases in the form of solid or liquid contamination, that will be captured by the matrix too, and subsequently it will be transferred to the next fluid. So let's see how this compromise is optimized, or not always possible with 100% optimizations, or rather optimize is something different, because compromising rather. So it's not possible to remove this particular contamination problem 100% in regeneration process. So depending on the type of process, if your subsequently heated gas in this process is fed back to the same system, then there is no problem, because contamination was there in the hot gas, source gas, and the contamination is partially transferred to the cold gas, because that will, after heating, heat is regained, and simultaneously that contamination is also partially, say in the hot gas it was 100%, but in cold gas it is say 40%. So obviously if you feed back that particular heated gas to the same system, then it doesn't make much difference, because the same contamination was already there previously. So this is basically the philosophy of this using regenerators, which is not possible for many processes. Like recuperative heat exchange is a common option for food processing, pharmacy industries, but regeneration can rarely be done due to this contamination problem. But in metallurgical heat extraction, many chemical heating process, and obviously power plant in mechanical purview, the heat wheels are very popular, because there the contamination is not that serious problem. So next, go to the next slide. Types of heat wheels. And here is, these heat wheels are basically defined on the basis of the matrix structure. The type 1 is metal frame packed with a core of knitted metal mesh. What is this knitted metal mesh? Is nothing other than you have Scotch-Brite and another which is called the steel wool in kitchen as a scraper of the utensils. So বাংলায় বললে বাসন ধুতে আমরা যে জিনিসগুলো ইউজ করি, rather in the kitchen for washing the kitchen, if it is highly sticky materials, say oil sticky things, then we use some steel wool sort of thing to remove those. Just consider that composition happens in the matrix of the knitted, that is called the knitted metal mesh. So why we use it? Idea is very clear. Because given a metal frame means what? You have a structure where holes are there. Now, if there are holes in the metal frame and gas passes through the holes, then obviously large amount of gas will pass through at the central part of the hole, which doesn't come in contact of the metal structure at all. So not much of heat transfer can happen. But if those holes are filled up with those sort of steel wool or other any metal wool, conducting metal wool sort of thing, then what will happen? When you pass, the gas passes, then effectively surface area of the heat exchange increases significantly, because those metal knitted metal mesh will increase the overall surface area of heat exchange. But simultaneously, remember, it will cause two problems. The first problem is basically it will provide some resistance to the fluid flow, so pressure drop will be higher. And number two is it will arrest any contamination, or rather most of the contamination, because the passage is filled up with this metal knitted mesh, means automatically most of the dust and liquid being carried by the gas will be arrested in that, and that will be subsequently transferred to the cold gas in the next cycle, or in the next process, better to say. So type 1, just let me discuss the all types, then I will just make the relative discussions of these all types. Type 2 is made of corrugated metal sheets called laminar flow wheel. What is the meaning? Corrugated sheets means you can just think about, most probably all of you have seen the poor people tin sheet in those so-called small houses. Or asbestos is not recommended currently, because asbestos is highly carcinogenic. So most of the cases the asbestos is avoided, but still I have found that some poor people still use the asbestos. But there you can find out it's corrugated, means it's a wavy structure. Why the wavy structure? Because very simple, then the rainwater can pass through these channels very easily. So this wavy structure of those metal sheets is called corrugated metal sheets. Now, if you put two corrugated metal sheets one after another, then in between two corrugations subsequently, there will be a small channel created. And interestingly, those, if you can create it less gap, more and more, then effectively the heat transfer can also increases. Plus side is lesser contamination during the flow of this corrugated sheet. But there is a restrictions with respect to the fluid flow condition. It will also provide sufficient resistance, and the flow type will be a laminar type flow. I don't know, all of you know the laminar and turbulent flow. That's why it's called laminar flow wheel. Laminar flow condition is very well structured flow, but effectively the heat transfer also decreases. So this corrugated metal sheets reduces contamination, but simultaneously heat transfer also decreases. Third one, we call it made of ceramic matrix of honeycomb configuration for up to very high temperature, 875 degrees Celsius. Honeycomb structure is what? The nature now teaches, we call it, nature is the greatest engineer and simultaneously greatest scientist and greatest artist also. And so we are trying to learn most of the modern engineering trend is go by nature. So for the storing of their honey, these honeybees has created their particular structure in their house, that's called a hexagonal structure in each of those small holes in their, whatever you call it, their house, actually the storage of that particular honey. Now, honeycomb structure has got a special structure of increasing the heat transfer surface area for a given volume. So, what is corrugated? What does the corrugated metal sheets? The honeycomb structure also does a similar thing, but simultaneously increasing more surface area for a given volume, as if this is a learning from the honeybees what they make it for their home, and we can extract more heat transfer without any effective increase of the contamination, because we are increasing the surface area for the same volume. But difficulty with this third type of matrix formation is the manufacturing of this honeycomb structure is not very easy for the metals, but it can be done partially with easier option by using the ceramics. But ceramics has got lesser heat transfer characteristics. So as I repeatedly telling, the engineers never get the best, they have to optimize. So these are usually, the honeycomb structure is not cost effective for using metal and for comparatively lower temperature, but this become rather economically feasible for those ceramic structure with for very high temperature applications. Okay, then what is the number 4? These are called hygroscopic wheel. What is the hygroscopic wheel? Here we are adding one more dimension to this particular system. What is that dimension? Any hot flue gas that is used as the heat source generally contains some moisture inside it, moisture being carried with that. Because any fossil fuel burning process means what will happen? Fossil fuels all composed of hydrocarbons. Carbon is one of the burning or other heat adding material, and hydrogen is another. What happens with carbon burning? That produces the carbon dioxide or carbon monoxide. But what happens with hydrogen? Moisture. So moisture at that high temperature is in the form of water vapor. Now, if it is in water vapor, so in the gas, though it is remaining in the moisture form, it is containing significant amount of latent heat. If you can convert that moisture into liquid effectively through the heat transfer, then it will give up its latent heat also, which is significant amount for a large moisture content gas. But through this heat transfer process, that substantial significant high amount of heat cannot be regained by the so-called moisture cooling process up to liquid state. So what is the option? Option is, in the passage of the matrix, if you provide some coating of hygroscopic that absorbs the moisture, even in the vapor form, if it absorbs the moisture, automatically it will gain the heat, latent heat of that moisture too. Example is also given, lithium chloride sort of material. Interesting part is, for this sort of hygroscopic material coating in the matrix, this adds up to significant heat gain and heat, release to the colder gas. But unfortunately, these hygroscopic materials are also exposed to the contamination and causing very immediate blockage of the passages. So nothing is better. Anyone is better with respect to one particular aspect, either cost or simplicity or etc. Another may be better with performance, but adding up some additional problems. So selecting a proper system absolutely depends on the proper judgment of the practicing engineers. And in any organizations or company, there is a traditional heritage of this knowledge of selecting into their system. I've seen, rather, I have consulted many power plants where the heat wheel selection has evolved, which one is better over many years, and having some loss and having some, very bitter experience, they have finally landed up with their practice of choosing that particular heat wheel. And I have found out that some companies have mentioned that we had some lot of, loss before we can come to our final selection. So there is nothing like a given recommendations, but there is a standard recommendations of those companies who sell these things, because they have to sell also and they have to convince their customer. But out of these 4 types of wheels, whatever we have mentioned, should I give a brief discussion, or you have understood it? Can I skip this discussion part? Okay, fine. So with these four different types of quills, we have found out that the first one being simple, but heat transfer is also low. I'm just mentioning in short so that you can note it. The second type, it's also the contamination is less. The first type, the contamination is also high. It is the low cost and simple option, the type 1. Type 2, low cost, simple option with lesser contamination but less heat transfer too, so that the performance is poor. Third one may not be always possible with metal structure and it becomes costlier, but effectively the performance is better. And the contamination is also not that great and not that more. But the type 4, significant heat transfer happens for the type 4 because with the hygroscopic material it absorbs the moisture, and through the moisture absorption it absorbs the latent heat of moisture in the flue gas too. But it has got a problem of severe contamination issue, and for operating hygroscopic material is a costly aspect because you have to replace those coatings after a operation for a smaller time because it gets contaminated, and those effectivity of those hygroscopic coating becomes ineffective for a small time, within a small time. Okay, so I could explain rather the four types. There are some more types, that is beyond my knowledge, or rather those who are in industry, they can suggest some more types, but I can just find out these four types of matrix that is used in heat wheels or regenerators. Any queries up to this? Okay, no queries, so I can go to the next slide. So this is nothing you have to rather draw or something like that, but I'm just showing you the three-dimensional figure because this I've seen shown in section. Now you can rather realize how the actual heat wheel operates. So there is some wheel is rotating by a motor. Okay, the motor drive with the belt pulley on the shaft of the wheel. It makes it rotate at a very low speed. What is the speed? That has to be find out from the simulation calculations of the heat exchange process. And then it has got two side-by-side passage with proper radial seal and the circumferential seals. Circumferential seal is to arrest the leakage of the same fluid from the upstream to the downstream side, but radial seals are used for arresting the leakage between the two heat exchanging fluids. And then we have the matrix structure inside, maybe any of the four types we discussed. It can be even more, that is beyond my knowledge. So out of these four, we have relatively discussed about the simplicity and the corresponding performance, cost, operational difficulty, etc. out of these four possible options of the matrix. Pictorially, it looks something like this. Actually, the physical picture I have got from one company, it looks something like this if you look from one of the sides. The wheels, this is a rather little bit blurred picture, but anyway, this physically looks like this. With this, I can just cover up one more very simple device. It is called run around coil. So what happens in the run around coil, if you can look into the picture, it's a very simple device, but very effective also. If you have two constant flows of gas specifically by two side-by-side channel, not very close, but little bit within manageable distance. Manageable means within some several feet, not more than that. Then what will happen? This is very common in air conditioning applications. Large scale air conditioning application, what is the idea? Idea is, say if it is air conditioning, can be either heating or cooling of air. Now look into if it is an heating applications for cold countries, then continuously you have to make the atmospheric air heated before it is being supplied to the confined space or room space. But in the process, you have to remove that heated air when it is at a higher temperature than the local atmosphere, and fresh air has to be brought in. Why fresh air? Otherwise, oxygen percentage will continuously decrease in the confined space because people are occupying the space and they are continuously taking oxygen. I mean, not only those people staying inside, but also, I mean, the other elements needs oxygen, which is the living elements. So you have to replace that, though the temperature is effectively still higher, but you have to reject due to oxygen concentration manage and other issues also. Some odor may be created for continuous use, etc. So if you don't replace that with fresh air, that problems will be there. So in air, but for our countries, tropical countries, the inside air is during summer when we use the air conditioning. Air conditioning usually in India we don't use the air conditioning during winter because the weather is rather heating is not required. It is not that much cold, but simultaneously, I mean during summer our temperature difference. I mean the high temperature is so high that it needs comfortable condition through air conditioning. Now in air conditioning, as some air from the inside space is being rejected, that is at a different temperature from the normal air that is coming in again, then obviously the normal air, if it is a cooling requirement, then that needs subsequent cooling before being transferred to the room space. So what you can do, the air being forced to reject to the atmosphere is lower than the atmosphere, and you need the cooling of the air coming, fresh air coming from the local atmosphere. So get the heat exchange between these two. So what will happen? Your effective temperature of the air will be cooled initially by the rejected air. What gain you are having then? The heat load. That means subsequent cooling. That is not enough to cool it up to the required temperature. But subsequent cooling will be less, which will be actually done by the so-called vapor compression refrigeration process. I'm not going into those in details because these are in the mechanical engineering course we teach. But if we initially, the common sense is we have to cool the air in tropical air conditioning process where air needs to be cooled for air conditioning. You have to cool the air from the high temperature of the atmosphere, local atmosphere, to the room temperature, which needs to be at a lower temperature. So this cooling process needs some energy input in the form of electricity. Now, if the temperature say outside at 40 degrees Celsius, inside temperature for the comfort condition is 20 degrees Celsius. So somehow you have to, in this air conditioning process, reduce the temperature from 40 to 20. Now the question is, if the entire cooling process is for 40 to 20 degrees Celsius temperature change, then corresponding electricity requirement or AC power consumption will be very high. What you can do, at least partially you can reduce it by exchanging heat between the rejected cooled air from the confined space with the fresh incoming air from the atmosphere. And then this heat transfer may not be always possible side by side because these two ducts may not be side by side. So to make this heat transfer, we use this runaround coil. This is very handy. Handy means you can see here the structure. We have a header tank. Header tank, the purpose of the header tank is nothing other than holding that particular stock of the working fluid. And it is rather not always using, but time to time it fills up if there is some leakage or some evaporations of this working fluid. Now you have a pump and two heat exchange coils. I should not call it cooling coils. So these are passing through. These coils are rather kept into two parallel flows of gases, one at higher temperature, another at lower temperature. Now you can find out that continuously through these coils, if the working fluid has to flow, this is generally liquid, then a pump is required, and the pump is required to make this effective heat transfer between these two sections. So this is as if the device is very simple. You need a pump, you need two heat exchanging surfaces located at two different streams with different temperature, and effectively at least some heat can be recovered in a sense. It can add to the form of required cooling load for the refrigeration process of the air conditioning where cooling is required. So just write down the run around coil. I've given the definitions. I hope that you have written it already. Alternately called liquid coupled indirect heat exchange network. Means this is basically heat exchange process coupled by what? Through a flowing liquid. So it is called liquid coupled indirect heat exchange, because indirect means what? Directly you are not bringing these two gases in contact. In its simplest form, it consists of standard extended surface fin tube. Do you have any idea what is fin? Fin? Fin means over the tubes you can put certain extended part which increases the effective heat transfer surface area. So for a given volume, to increase the heat transfer, you have to add some extended part over those tubes through which you want the actual heat transfer. So these are called fin tubes. And fin tubes, water coils used with a circulating pump. Generally, the working fluid used water, but obviously this can be replaced with, has to be replaced with other working fluids depending on the temperature of the heat exchange process. If the surrounding temperature, say sub-zero temperature, then water will not be an effective fluid at all. We have to use different additives to the water to decrease its freezing point. Okay. Then in the exhaust gas stream, and the other is located in the airflow that has to be preheated. It can be heating purpose, it can be cooling purpose. Then just add up one or two sentences. This runaround coil is considered to be useful for specifically HVAC, means heating, ventilation, and air conditioning applications at a low cost but not very high performing device too, because it's some sort of handy device. It's not a very effective like regenerator or heat wheels. It's a much costlier equipment. Heat pipe is also a costlier equipment because these needs specific design with specific material, regular maintenance, all these things. But that's why these previous two types are employed for more important and larger industrial applications. But these are effectively some sort of partial heat recovery, some sort of concept of chalega, some sort of in Hindi we call it, because this will give certain at least compensations of the heat gained, or rather overall energy efficiency. But this is not very effective also, because the amount of heat transfer in this process between two coils is not substantial or significant. So that just write down at the conclusion. Runaround coils are generally used for HVAC, H capital, V capital, A capital, C capital. The full term, if you just want to write, heating, ventilation, and air conditioning. Applications. Full stop. This device is popular. This device is popular due to its simplicity, of operation, and low investment requirement. Due to its simplicity of operation and low investment requirement. Full stop. However, performance of runaround coils is also poor and it contributes to only small heat recovery contributes to small heat recovery with smaller investment too. TWO, with smaller investment too. Full stop. As the effective device of this as the effective device of this system, is only a pump is only a pump its operation and maintenance are also simpler. Hence, next sentence, hence runaround coils are useful as auxiliary devices, AUXILIARY, auxiliary devices for waste heat recovery in only a few limited applications, comma, mostly HVAC applications, heating, ventilation, and air conditioning applications. Okay, so today I wind up here because it will be difficult to cover up any more device today. Let me see what is the next one. No, this I will not discuss. Plate heat exchanges, and then we have, yes, the pebble bed. I may discuss little bit. This is important and interesting also. And then no, recuperative burners you will not be able to understand. Economizer I may skip anyway. So there are some few more devices I will start next class from, because it's not possible to start a new device. Any queries up to this? Whatever you have discussed. Generally there is no query. Today also same thing, so I can stop presenting and make the roll call. Tomorrow also we'll have the class on the same time, that means 8 to 9:30. This week I have some outside engagement. Anyway, I can manage the class also. Today is 5/11. Okay. Sheikh Muhammad Ali? No. Dipendu Gupta? No. Dipendu Gupta is generally present. Why is he anyway absent today? Shaunak Agarwala? No. Anubhav Shah? No. Gitan Dash? No. Vaibhav Agarwal? No.